The initiation and control of aircraft electrical circuits is achieved by switches and relays. The operation of relays is covered in another lesson. There are a large number of different switch types in use on aircraft. They include manually operated switches, microswitches, proximity detectors, time switches, bimetallic switches, and centrifugal switches. In this lesson, we will look at manually operated switches. However, before we look at the various types of typical aircraft switches, it is important to know what defines an electrical switch and how it functions. An electrical switch is a mechanical device that connects and disconnects an electrical circuit. In its simplest form, the switch has two pieces of metal, called contacts, that touch to make the circuit. A pair of contacts is said to be closed when there is no space between them, allowing electrical current to flow from one contact to the other. When the contacts are separated by an insulating air gap, they are said to be open, and no electrical current can flow. It is worth noting that this terminology is the opposite of that used in hydraulic systems, where a closed valve prevents the flow of fluid and an open valve permits flow. A manually operated switch may be a toggle switch, a rocker switch, a push-pull switch, or more probably on modern aircraft, a switch light. The simplest toggle switch is a two-position switch with a single pair of contacts. With this type of switch, the contacts can be either closed or open. Here, you can see a number of two-position toggle switches being used to control the exterior lights on a Boeing 747. Three-position toggle switches normally have a center-off position, with the electrical power able to go to one of two services depending on the direction in which the switch is moved. This switch here, for instance, allows the pilot to select either both the upper and lower anti-collision beacons, or the lower one only. Toggle switches, depending on type, can remain in the last selected position, as all the light switches we have seen so far do, or they can be fitted with springs, so that when the operator's finger is removed, the switch moves back to the off position. These Boeing 747 pressurization outflow valve control switches are typical examples of sprung switches which return to off when released. Some toggle switches may be fitted with guards to prevent inadvertent operation. Guards are normally fitted to switches which are only operated in abnormal or emergency situations. This generator disconnect switch, for instance, is guarded to the off position. To operate the switch and disconnect the generator, the guard has first to be raised. Rocker switches operate in exactly the same manner as toggle switches, the only difference being the shape of the operating mechanism. Push and pull switches are normally only two-position, so the contacts in this type of switch are either open or closed. The switch is operated by pushing or pulling on the stem of the switch. Switch lights have largely replaced the other switch types in modern aircraft, and combine the functions of a switch with a push action and an indicator light for the associated function. As with toggle switches, switch lights may be of the momentary action type, where the switch light is pressed and held to activate the service, and released to deactivate it. Or they may be of the alternate action type, where the switch light is pressed once to activate a service and pressed again to deactivate it. The face of the switch light is used as an indicator, and depending on switch function and system status, any one of numerous indications may be displayed on it. For instance, on this typical Boeing fuel control panel, the fuel pump switch lights have on lights which illuminate when the associated pump is switched on and operating, and low pressure lights which illuminate should the pump fail. Some switch lights use flow bars to join lines on a schematic diagram to indicate flows. Flow bars are used here in the crossfeed valves to indicate when they are open. Should a crossfeed valve fail, then the flow bar will be replaced by an amber valve caption. Again, as with toggle switches, switch lights used to operate important abnormal or emergency services may be guarded to prevent inadvertent operation. In this case, the guard is a transparent perspex panel, which is hinged at the top and drops over the switch light. To operate the switch light, the guard is first raised, then the button can be pressed. The guarded switch lights shown here control the Boeing 767 aircraft's fuel dump system. That is the end of the lesson on manually operated switches. Here is a summary of the important points. Toggle and rocker switches can be 2 or 3 position. Switch lights combine the functions of a switch and an indicating light. Toggle switches, rocker switches and switch lights can be of the momentary action type, where the switch is only closed while the operator maintains finger pressure, or they may remain in the selected position until another selection is made. Both toggle switches and switch lights can be guarded to prevent inadvertent operation. In this lesson, we will discuss the automatically operated switches which may be found on an aircraft. They include microswitches, proximity detectors, time switches, bimetallic switches, and centrifugal switches. We will examine each of these types of switch, beginning with microswitches. Microswitches are used in modern aircraft to detect the position of a particular device, although on landing gear installations they have largely been replaced by proximity detectors. A microswitch operates in the same manner as a momentary action switch light, except that instead of the switch being operated by the pilot's finger, it is fitted with a plunger, which operates the switch when it comes into contact with a striker plate fitted to the component being monitored. In the typical example shown here, the moving contact is on a spring arm, which will hold it against the upper contact. When the component being monitored reaches the required position, the striker plate will push down on the plunger, causing the moving contact to move down and connect with the lower contact. Shown here is the Boeing 747 flap lever, which has a number of microswitches fitted to warn the crew of flap failures. Bimetallic switches are temperature-sensitive switches, which operate when a certain temperature is reached to provide an indication to the pilot or to activate or deactivate a circuit. The switch consists of a bimetallic strip made up of 2 strips of dissimilar metals bonded together. The strip is fixed at one end, with the other end free to move up and down. The free end has an electrical contact on it. At normal temperatures, the strip is straight. In our example shown here, when the strip is straight, its contact is touching a fixed contact. When the switch is heated, the 2 metals will expand by different amounts, and the bimetallic strip will bend. This causes the contacts to open, breaking the electrical circuit. Bimetallic switches are often used in battery charging circuits. The switch is placed in close proximity to the battery to monitor its temperature. Should the battery temperature become excessive, the switch will operate to shut off the charging current and put on a warning light. Proximity detectors are electrical or electronic sensors that respond to the presence of a material. The electrical or electronic response is used to activate a switch, relay, or transistor. There are many types of proximity detectors. The major types are inductive, capacitive, and magnetic. The inductive and magnetic sensors need the monitored target to be metal, but the capacitive type can monitor either metal or non-metal materials. The first type of proximity sensor that we are going to look at is the inductive type. Inductance is a property that a coil has when it has an alternating current or AC pass through it. Inductance is fully explained in the AC part of the syllabus. For the moment, all you need to know is that the inductance of a coil with AC passing through it changes when it is brought into close proximity to a suitable ferrous material, and that this change can be measured. It is important on aircraft with retractable landing gear systems that the pilot is kept informed of the position of the landing gear. On older aircraft, this is achieved by using gear-operated microswitches to operate indicating lights. On modern aircraft landing gear, inductive-type proximity sensors are used instead of microswitches. In a typical undercarriage system, each proximity sensing unit will consist of 3 components. An electronic circuit, which is contained in a component known as the landing gear accessory unit. This circuit is able to sense changes in inductance and switch the appropriate gear light on and off in response to these changes. A sensor, consisting of an AC coil located on an appropriate landing gear structure, and a ferrous metal target for each sensor. When the part of the gear being monitored is in the correct position, the target and the sensor are in close proximity to each other. This changes the inductance in the coil, and the electronic circuit will then produce the appropriate indication. The inductive proximity sensor is a hermetically sealed unit and is actuated by the presence of the actuator or target. It is not touched by it. There are no moving parts. As a result, this type of switch is unaffected by atmospheric conditions and is highly reliable. Now we will look at the capacitive type of proximity sensor. Capacitance is a property that 2 plates of a suitable material placed in close proximity to each other have when an alternating current is applied to them. Once again, this is fully explained in the AC part of the syllabus. For now, all we need to know is that the capacitance of the plates will vary if the gap between them is filled with different materials, and that this change in capacitance can be measured. Capacitance-type detectors can detect changes in all materials, both solid and liquid. They are widely used in aircraft fuel quantity measuring systems. A typical capacitive fuel measuring device consists of 2 concentric tubes of metal with an AC supply across them, standing upright in the fuel tank. The gap between the 2 tubes will be full of air when the tank is empty, and full of fuel when the tank is full. At intermediate fuel levels, the gap will have part fuel and part air. The capacitance of the device will change as the proportion of fuel and air changes. This capacitance is measured and displayed on a gauge as fuel quantity. The final type of proximity detector that we are going to look at is the magnetic type. Once again, magnetism is a subject which is covered fully later in the syllabus. We will take a very quick look here at the properties of magnets, only in sufficient depth to see how this type of detector works. A bar magnet is a metal bar which displays magnetic properties. One of the properties of a magnet is that it is surrounded by a magnetic field. The lines of force or flux of the field come out from one end or pole and return to the magnet at the other end. If a coil of wire is moved through this field, cutting through the lines of flux, an electromotive force or EMF will be induced in the coil. If both the coil and the magnetic field are stationary, no EMF will be induced. There has to be relative movement between the lines of flux and the coil for an EMF to be induced. Another property of a magnet is that if a suitable ferrous material is placed near a pole, the magnetic field will flow through that material before returning to the opposite pole. It is these two properties that are used in the magnetic proximity detector. In a simplified magnetic proximity detector, a coil is wound around a bar magnet, and one pole of the magnet is then located close to a ferrous object. If the ferrous object moves, the magnetic flux changes, causing the force lines to move through the coil, and an EMF is induced. If a number of ferrous objects move past the magnet, a train of pulses is induced in the coil. The speed or frequency of this train of pulses can be measured. Magnetic detectors are most commonly used in conjunction with mild steel gear wheels, each tooth in the wheel being, in effect, a ferrous object. The detector is located close to the periphery of the wheel and provides an output having a frequency equal to the frequency of passage of the teeth past the detector. This frequency will be proportional to the speed of rotation of the wheel, so it can be displayed on a gauge calibrated in revolutions per minute, or RPM. Time switches or relays can be initiated electrically or mechanically to activate a circuit after a specific time interval has occurred. A time switch is often found in an aircraft's auxiliary power unit, where it will close the air intake door after a specific time delay after the auxiliary power unit has been shut down. Time switches can be simple wind-up mechanical switches, like this galley hot cup controller, or, more probably, on modern aircraft, solid-state electronic devices. Centrifugal switches can be set to activate or deactivate a circuit as the rotational speed of a device increases or decreases. In the simplified diagram shown here, the flyweights are being driven around by the component whose rotational speed is being monitored. As the speed increases, the flyweights move out, pushing the non-rotating sleeve against the spring, which in turn moves the lever arm. At a specific rotational speed, the lever arm will close the switch contacts and an electrical signal will be sent. Centrifugal switches are commonly used to switch off engine starter motors once the engine reaches self-sustaining speed. That is the end of the lesson. Here are the main points. Microswitches are mechanically operated by a striker plate on the component being monitored. Bimetallic switches are temperature-sensitive switches, which operate when a certain temperature is reached. Proximity detectors are electrical or electronic sensors that respond to the presence of a material. They have no moving parts. Inductive and magnetic sensors respond to the proximity of ferrous materials, but capacitive sensors respond to all materials. Time switches or relays can be initiated electrically or mechanically to activate a circuit after a specific time interval has occurred. Centrifugal switches can be set to activate or deactivate a circuit as the rotational speed of a device increases or decreases. In an electrical circuit, abnormal conditions may arise which can cause the current or the voltage in the circuit to become excessive. A short circuit, for instance, will lead to a large increase in current, causing the cables carrying the current to overheat and possibly catch fire. Generators need to be protected from faults in individual loads, so that a fault in one load will not cause the generator to fail, with a subsequent loss of other loads. The most commonly used electrical circuit protection devices are fuses and circuit breakers. They both protect against excess current and are rated in amperes. The fuse or circuit breaker is placed in series with the load that it is monitoring. Their rated current is the maximum current that they can carry continuously without blowing or tripping. A fuse is said to have blown when its conducting element melts. A circuit breaker is said to have tripped when its contacts move apart, breaking the circuit. The difference in the type of protection provided by fuses and circuit breakers is in their time of operation, relative to the attainment of maximum fault current. A fuse will blow in a shorter time than it would take for a circuit breaker to trip. In both cases, the time taken is measured in fractions of a second. But this can be important for pieces of sensitive electronic equipment, which are often individually protected by fuses. A fuse, once blown, must be discarded and replaced. This should be done once only. If the fuse blows again, the fault must be investigated and corrected before a further replacement fuse is fitted. It is important always to replace a fuse with one of the correct rating. Using a replacement fuse of a lower rating will cause it to blow prematurely, while using one with a higher rating will leave the circuit vulnerable to excessive current and the subsequent risk of overheating. It is an EASA regulatory requirement that an operator shall not operate an aeroplane in which fuses are used unless there are spare fuses available for use in flight equal to at least 10% of the number of fuses of each rating, or 3 of each rating, whichever is the greater. Unlike the fuse, a circuit breaker may be reset after it has tripped. Like the fuse, this should be done once only. If the circuit breaker trips again, the fault must be investigated before a further reset is attempted. A circuit breaker may also be used as a circuit isolation switch by manually tripping and resetting it as required. That is the end of this introductory lesson on circuit protection devices. Here are the main points you should take from the lesson. Blown fuses have to be discarded, but a tripped circuit breaker may be reset once the fault has been rectified. Fuses and circuit breakers are rated in amperes. It is a regulatory requirement that an operator shall not operate an aeroplane in which fuses are used unless there are spare fuses available for use in flight equal to at least 10% of the number of fuses of each rating, or 3 of each rating, whichever is the greater. In this lesson, we will look at the fuses that are used to protect an aircraft's electrical system. There are 3 types of fuse commonly used on aircraft. They are the cartridge fuse, the high rupture capacity or HRC fuse, and the current limiter fuse. Fuses cannot be reset and must be discarded and replaced if they blow or rupture. We will begin by looking at the cartridge fuse. The cartridge type fuse consists of a tubular glass or ceramic body with a fuse element suspended between two brass end caps. The fuse element may be made from tinned copper wire, silver wire, or electro-tinned zinc. Zinc is generally used in heavy-duty circuits. Fuses are usually fitted in fuse holders with screw-on caps. The fuse is a tight fit in the end cap, so as the cap is taken off, the fuse will come out of the holder with it. A fuse blows when the current flowing through it is sufficient to melt the wire or strip element, the time taken varying inversely with the current. All fuses are rated at a specific current value in amperes. The rating indicates the current they will carry continuously or intermittently without unduly heating up or deteriorating. The rating of a fuse for a particular circuit is such that the fuse will blow at a current level below the safety limit of the equipment or cable being protected. For this reason, only a fuse of the specified current rating should be used in a particular circuit. The ratings of aircraft fuses can vary between 0.5 and 500 amperes. At the higher ratings, high rupture capacity fuses are used. The high rupture capacity, or HRC fuse, is an improvement on the cartridge type fuse. It is used mainly in high current rated circuits. It consists of a tubular ceramic barrel within which a number of identical fuse elements in parallel are connected to end caps of plated brass or copper. The barrel is filled with powdered marble or clean quartz sand to damp down the explosive effect of the arc setup on rupture of the fusible elements. The high rupture capacity fuse has the following advantages over the normal glass cartridge type. It blows at a more accurate current flow. It blows without flame. It does not deteriorate with age. It is more robust. And it is not affected by ambient temperature. Current limiters, or air fuses, are fuses which are again used in high current circuits. They are designed in such a way that they can carry a considerable overload current for a short period of time before blowing or rupturing. Their application is confined to the protection of heavy-duty power distribution circuits. The output of a transformer rectifier unit will be a prime location for a current limiter to be used. Transformer rectifier units are described fully in the alternating current series of lessons. A typical current limiter incorporates a fusible element, which is, in effect, a single strip of tinned copper, drilled and shaped at each end to form lug-type connectors, with the central portion wasted to the required width to form the fusing area. The central portion is enclosed by a rectangular ceramic housing, on one side of which there is an inspection window, which, depending on the type, may be glass or mica. The wasted portion can be viewed through this window, so it can be seen when the fuse has blown. If it is necessary to isolate a particular circuit by the removal of the fuse, in order that the system be made safe, or for work to be carried out, a dummy fuse or fuse holder should replace the fuse which has been removed to warn personnel not to fit a normal fuse. Dummy fuses are manufactured to standard fuse dimensions from red plastic. the centre portion being square in section with corrugated sides to facilitate identification. To distinguish the dummy fuse when it is in the holder, a red streamer is attached to it. That is the end of the lesson. You should remember the following key points. Fuses cannot be reset and must be discarded and replaced if they blow or rupture. Fuses are rated in amperes. Current limiters are designed in such a way that they can carry a considerable overload current for a short period of time before blowing or rupturing. Dummy fuses are red in colour with corrugated sides. When in use, they should have a red streamer attached. In this lesson, we will look at circuit breakers, which have mostly replaced fuses as the circuit protection devices in both direct current and alternating current circuits on modern aircraft. Circuit breakers combine the function of fuse and switch. They can be used for switching circuits on and off in certain circumstances. Generally, the circuit breaker incorporates an automatic thermosensitive tripping device. Once tripped, a circuit breaker usually has to be reset manually. Circuit breakers can be tripped and reset any number of times, but remember that a tripped circuit breaker should only be reset once. If it trips again, the fault must be dealt with before another reset attempt is made. Some larger circuit breakers may also include electromagnetic and reverse current tripping devices. As with fuses, circuit breakers are current protection devices and are rated in amperes. Small single-button circuit breakers are rated from 1 to 45 amperes, whereas large circuit breakers can be rated up to 600 amperes. The flight deck of a modern aircraft will have a circuit breaker panel or panels, where numerous small single-button circuit breakers will be located. These circuit breakers fall into two groups, known as trip-free and non-trip-free circuit breakers. If a non-trip-free circuit breaker is held in by the pilot under fault conditions, the circuit will be made. This is clearly dangerous. If a trip-free circuit breaker is held in under the same circumstances, the circuit cannot be made. Almost without exception, the circuit breakers on the flight deck of your aircraft will be of the trip-free type. In a typical trip-free circuit breaker, as shown here, a latch mechanism is being controlled by a thermosensitive tripping device, in this case a bimetallic strip. With the circuit breaker in the closed position, current flows through the main contacts, through the bimetallic strip and onto the load. If the current flow becomes excessive, the bimetallic strip will bend as shown, opening its contacts and releasing the latch mechanism. This action will open the main contacts and cause the push-pull button to pop out, exposing a white band on the button shank to aid identification of the tripped circuit breaker. If an immediate reset attempt is made, the current will not flow in the circuit, because the bimetallic strip contacts will still be open, and the button will not latch in. Only when the bimetallic strip has cooled sufficiently will the circuit be able to be completed again. This type of circuit breaker can be used as a switch by pulling out the button. This will override the latch mechanism and open the main contacts. If a circuit breaker has been pulled for maintenance purposes, then a clip with a red flag attached is affixed to the shank to warn personnel not to reset it. Larger current capacity circuit breakers may have both a trip and a reset button. These circuit breakers are not normally accessible from the flight deck. Reverse current circuit breakers, or RCCBs, are fitted in direct current circuits. To prevent the battery from attempting to drive the generator as a motor, if the generator contactor should fail closed, when the generator is not producing a power supply. The generator contactor is usually opened by the generator cutout when it senses a reverse current flow. This is fully explained in the lesson on DC generators. In order not to interfere with this process, the reverse current required to operate a reverse current circuit breaker is high, usually more than 200 amperes. The reverse current circuit breaker contains a latch mechanism, which is holding a set of contacts closed. The latch mechanism is held closed magnetically. A coil wound around the latch mechanism produces a magnetic field, which helps to hold the mechanism latched when the current flow is in the normal direction. However, when the current flow through the coil is reversed, its magnetic field operates in the opposite direction. At a preset current level, this field will have sufficient force to break the latch and open the contacts. Once tripped, an RCCB can only be reset by pushing the manual reset button. There is usually also a manual trip button on the unit. That is the end of the lesson. Remember the following key points. Circuit breakers are rated in amperes. Flight deck circuit breakers are usually trip-free thermally tripped circuit breakers, which need to be reset manually. A trip-free circuit breaker can only be reset once the fault has cleared. Holding in the reset button will not allow current to flow in the circuit. In the event of a circuit breaker trip, only one reset should be attempted before the defect is investigated. Small circuit breakers fitted in the flight deck are sometimes used as switches. Reverse current circuit breakers prevent large reverse current flows in direct current circuits. In this lesson on capacitors, we will discuss what capacitance is and what a capacitor is made of. We will state the units of capacitance and examine how capacitors act in a direct current or DC circuit. We will also take a quick look at capacitors in alternating current or AC circuits. However, capacitance in AC circuits is fully covered in the lessons on AC. A capacitor is a device that stores electrical energy in the electrical field that can be created between two conductors that are separated by an insulator. In its simplest form, a capacitor consists of two metal plates separated by an insulating material called a dielectric. Wires connected to the plates allow the capacitor to be connected into an electrical circuit. If we connect one plate to the positive terminal of the power source and the other to the negative, electrons will flow to the plate attached to the negative terminal and will be drawn from the plate attached to the positive terminal. There will be no flow across the insulator, but one plate will become negatively charged with extra electrons, and the other positively charged because of a shortfall of electrons. The attraction between the oppositely charged plates will produce an electrical field across the dielectric. In this electrical field, the electrons in each atom of the dielectric are attracted to the positive charge and repelled by the negative charge in the manner shown. However, they are too firmly attached to the nucleus for any to escape. Once the charge voltage across the plates equals the supply voltage, the flow of electrons will stop. If the capacitor is now removed from the supply, it will retain this charge until it is connected to an external circuit. When the surplus electrons on one plate will flow through to replace the shortfall on the other, and the atoms in the dielectric will return to their original shape. If we place a capacitor in a direct current circuit, as shown, when the switch is placed to position A, the capacitor will be connected to the power supply. The ammeter will initially show high flow, then fall to zero. We can see from this that in a DC circuit, apart from the initial charging current, a capacitor blocks current flow. When the switch is moved to position B, the capacitor will now discharge through the resistor, and the ammeter will once again show a high flow, which will fall to zero. Much of the electrical power used on aircraft is alternating current, or AC. In AC systems, the polarity of the supply voltage changes cyclically. The change happens at a much greater rate than shown here. In fact, in aircraft AC systems, it changes 400 times every second. If a capacitor is placed in an AC circuit, it will constantly be charged and discharged as the polarity of the supply changes. So electrons will constantly be flowing to and from the plates of the capacitor. Although no current flows across the capacitor, current is constantly flowing in the wires, and if a light bulb is placed in the circuit, it will remain illuminated. From this, we can deduce that a capacitor appears to allow current to flow freely in an AC circuit. Capacitance is the ability of a capacitor to store electrical charge. The unit of capacitance is the farad, F. In terms of capacitance, the farad is a very large unit. A 1 farad capacitor could be as large as a Coke can. The farad is therefore subdivided into smaller, more convenient units. 1 microfarad is 1/millionth of a farad. 1 nanofarad is 1,000th of a millionth of a farad. And 1 picofarad is 1/millionth of a millionth of a farad. Capacitors are also rated by their working voltage. This is the largest DC or peak AC voltage which can be applied across the capacitor. It is usually marked on the case of the capacitor, and if it is exceeded, the dielectric may break down, permanently damaging the capacitor. There are 3 factors that affect the capacitance of a capacitor. These are the area of the facing plates, the distance between the plates, and the material of the dielectric. It is fairly obvious that the larger the area of the plates, the more electrons can be stored on them, so capacitance will vary directly with plate area. The distance that the plates are apart determines the strength of the electrical field between them. If the plates are widely separated, the electrical field will be weak, and it will not pull many electrons onto the negative plate. If, however, the plates are very close together, the attraction caused by the unlike charges will produce a strong field, and lots of electrons will be attracted. So capacitance varies inversely with the distance between the plates. The third thing that affects capacitance is the material of the dielectric. Different dielectric materials have different effects on the electrical field, and this will give different values of capacitance. In order to compare different materials, they each have what is known as a dielectric constant, or K. The standard is air, and it has a dielectric constant, or K value, of 1. Waxed paper is a commonly used dielectric. It has a K value of about 3. So a capacitor having wax paper as its dielectric would have 3 times the capacitance of the same capacitor having air as its dielectric. Mica is another commonly used dielectric. It has a K value of about 5.5. Capacitors can be either of a fixed or variable capacitance, and they may be polarized or non-polarized. A polarized capacitor can only be used in DC circuits, and it must be connected in the correct direction in the circuit. If it is connected wrongly, it will almost certainly be damaged beyond repair. A non-polarized capacitor can be used in either DC or AC circuits, and can be connected in either direction. These are the circuit symbols for polarized and non-polarized fixed capacitors. Variable capacitors can have their capacitance varied either manually or automatically. A typical variable capacitor has a set of fixed plates and a set of rotating plates, so that the amount of overlap between the plates, and thus the capacitance, can be changed. This is the circuit symbol for a variable non-polarized capacitor. Next to it is the symbol for a preset capacitor, which can have its capacitance adjusted by maintenance personnel. Here is a summary of the electrical circuit symbols used for the various types of capacitor. Familiarize yourself with them before moving on. If capacitors are connected in parallel, they will act as one large capacitor, with the total area of the plates equal to the sum of the areas of the plates of all the parallel capacitors. Thus, the total capacitance of a number of capacitors in parallel can be found by adding together the individual capacitances. In the example here, there are 3 capacitors in parallel. The total capacitance will be C1 plus C2 plus C3. That is 1 plus 0.5 plus 0.7, which is 2.2 farads. When capacitors are connected in series, the distance between the plates is effectively increased, and therefore the total capacitance is decreased. The total capacitance is found by using the same formula that we used for resistances in parallel. So, 1 over the total capacitance is equal to 1 over capacitance 1 plus 1 over capacitance 2, and so on. In the example here, we have 3 capacitors in series. To calculate the total capacitance, we use the formula. So, 1 over the total capacitance equals 1 over 1 plus 1 over 2 plus 1 over 3, or 6 over 6 plus 3 over 6 plus 2 over 6. That is 11 over 6. The total capacitance then is 6 over 11, or 0.55 farads. In a DC circuit, a capacitor is used in much the same way as an accumulator in a hydraulic system. It stores electrical energy which can be fed back into the system when required. That is the end of the lesson. Here are the main points you should take from it. A capacitor is a device that stores electrical energy in the electrical field that can be created between two conductors that are separated by an insulator. In a DC circuit, apart from the initial charging current, a capacitor blocks current flow. A capacitor appears to allow current to flow freely in an AC circuit. The units of capacitance are the farad, the microfarad, the nanofarad, and the picofarad. Capacitance varies directly with plate area. Capacitance varies inversely with the distance between the plates. Different dielectric materials give different values of capacitance. Finally, the formulas for calculating the total capacitance for capacitors connected in series and in parallel are on the bottom of the screen. The purpose of the main battery in an aircraft is to provide an emergency source of electrical power when the generator is not running, and to provide power to start the engine or the auxiliary power unit. Batteries are also used in emergency lighting systems and in torches. A battery is made up of a number of cells, which convert chemical energy into electrical energy by a transfer of electrons from one material or electrode to another, through a chemical known as an electrolyte, causing a potential difference or voltage between the two electrodes. During the transfer of electrons, the chemical composition of the two materials changes. The cells of a battery can be split into two types, known as primary cells and secondary cells. In this lesson, we will look at primary cells. A primary cell consists of two electrodes, immersed in a chemical called an electrolyte. The electrolyte encourages electron transfer between the electrodes until there is a potential difference between them. When the electron transfer ceases, the cell is fully charged, and the potential difference is approximately 1.5 volts between the two electrodes. When the positive and negative terminals of the electrodes are connected to an external circuit, electrons flow from the negative terminal to the positive terminal through the circuit. At the same time, more electrons are allowed to transfer inside the cell from the positive to the negative electrode. As this circulation of electrons continues, the negative electrode slowly dissolves in the electrolyte. When all of the chemical energy is used up, the potential difference will fall to zero. The process cannot be reversed, so the cell must now be discarded. Most aircraft torches use single-cell batteries of the primary cell type. A typical primary cell is shown here. The central carbon rod is the positive electrode, and the zinc plate case forms the negative electrode. The electrolyte between the electrodes is in the form of a paste, so batteries of this type are often referred to as dry cells. That is the end of the lesson. You now know that a battery is made up of a number of cells, which convert chemical energy into electrical energy. You also know that primary cell batteries cannot be recharged and need to be discarded once their chemical energy has been used up. In this lesson, we will look at secondary cells, which are the type found in aircraft main batteries. We will look at how these cells can be joined together to form batteries with different voltages and current supplying capabilities. Secondary cells work on the same principle as primary cells. They have two electrodes immersed in an electrolyte. The chemical reaction between the electrodes and the electrolyte causes a potential difference to build up between the two electrodes. When the positive and negative terminals of the electrodes are connected to an external circuit, electrons flow from the negative terminal to the positive terminal through the circuit. At the same time, more electrons are allowed to transfer inside the cell from the positive to the negative electrode. As this circulation of electrons continues, the chemical makeup of the electrodes and the electrolyte changes. When all of the chemical energy is used up, the potential difference will fall to zero. The difference between a primary cell and a secondary cell is that in a secondary cell, the process can be reversed. The chemical energy in the cell can be restored, and the changes in the composition of the electrodes can be reversed by passing a charging current through the cell in the reverse direction to that of the discharge current. This current is forced through the cell by applying a potential slightly greater than the cell potential to the cell in order to reverse the flow of electrons in the cell. In this way, the secondary cell can be discharged and recharged many times. The capacity of a cell is a measure of how much current it can provide for a specific period of time. Capacity is measured in ampere hours, or Ah, and is determined by the surface area of the electrodes, or plates as they are often called. The larger the area of the plates, the greater is a cell's capacity. There may be a number of plates joined together in parallel in each cell to increase the capacity of the battery. The groups of positive and negative plates are slotted together to form a cell. A cell with a capacity of 80 ampere hours, for instance, should theoretically provide a current of 8 amps for 10 hours, or 80 amps for 1 hour. In practice, the capacity will reduce as the rate of discharge is increased. A cell's rated capacity is normally measured at the 1-hour rate. We will now look at how cells can be connected together to form batteries of different voltages and capacities. On the screen is the symbol used in electrical circuits to depict a cell. The long line is the positive terminal and the short line the negative. A single-cell battery may be used on its own, or cells may be connected in series or in parallel, depending on the voltage and capacity required. For cells connected in series, the positive terminal of one cell is connected to the negative terminal of the next, and so on. The total voltage is the sum of the individual cell voltages. So, for instance, if 3 2-volt cells, each with a capacity of 10 ampere hours, are joined in series, they will produce a voltage of 6 volts. But the capacity will be the same as for a single cell, in this case 10 ampere hours. If the same 3 cells are connected in parallel, that is to say, the positive terminals are joined together and the negative terminals are joined together, then the total voltage will be that of one cell, 2 volts. but the capacity will be the sum of the individual cell capacities. In this case, 30 ampere hours. The cells can also be connected in a combination of both series and parallel, allowing both the voltage and the ampere hour capacity to be increased. As an example of this, if we take 4 2-volt cells, each with a 10 ampere hour capacity, and connect them as shown, you can see that we have 2 pairs of cells in series, with the pairs being joined together in parallel. We add the series voltages together to get the output voltage, in this case 4 volts. And we add together the parallel capacities to ascertain the total capacity, in this case 20 ampere hours. As we have previously said, a battery consists of a number of cells connected together. If 2 or more batteries are connected together, then the same rules apply as for the joining of cells. So if 2 12-volt 80 ampere hour batteries are connected in series, they will act as a single 24-volt 80 ampere hour battery. But if they are connected in parallel, they will act as a single 12-volt 160 ampere hour battery. That is the end of the lesson. You have learned the following key points. A secondary cell can be discharged and recharged many times. The capacity of a cell is a measure of how much current it can provide for a specific period of time. It is measured in ampere hours. If cells or batteries are connected in series, the total voltage is the sum of the individual cell or battery voltages, but the capacity is that of a single cell or battery. If cells or batteries are connected in parallel, the voltage is that of one cell or battery, but the capacity is the sum of the individual cell or battery capacities. An aircraft's main battery is made up of a number of secondary cells joined together in series to produce the required voltage. There are 2 types of secondary cell battery in common use. They are the lead-acid and the alkaline types. We will first look at the 2 types of battery, beginning with the lead-acid type. We will then look at how the condition of the battery is checked and maintained. One of the most common types of secondary cell battery is the lead-acid battery. The on-load voltage, or the voltage with a load being taken, of each cell of a fully charged lead-acid battery is 2 volts. The on-load voltage is also known as the nominal voltage. The off-load voltage, or voltage with no load applied, is 2.2 volts. A 12-volt lead-acid battery consists of 6 cells connected in series, and a 24-volt battery of 12. The active material of the positive electrode, or plate, is lead peroxide, and that of the negative plate is spongy lead. Both plates are immersed in an electrolyte solution of water and sulfuric acid. The liquid level should be just above the top of the plates. The container is glass, or more usually hard plastic, with a filler cap to allow topping up with distilled water to replace water which is lost through evaporation during use. A vent hole in the cap allows the escape of hydrogen gas, which is produced when the cell is working. The state of charge of a lead-acid cell can be determined by measuring the strength of the electrolyte solution. This is done with a hydrometer, which measures the specific gravity. The specific gravity of a liquid is defined as its weight divided by the weight of an equal volume of water. A fully charged cell will have a specific gravity of 1.27. When the cell is connected to an external circuit and current is flowing, the acid becomes weaker and its specific gravity falls. The voltage also slowly reduces. When the specific gravity has fallen to 1.17 and the voltage to 1.8 volts, the cell should be recharged. To charge a cell, it is connected to a battery charger, which applies a slightly higher voltage to the cell and causes current to flow in the reverse direction through the cell. The current flow causes the chemical constitution of the electrolyte to change, producing an increase in its specific gravity back to 1.27. When charging a lead-acid battery, it is important that the rate of charge is controlled. Charging too quickly can cause gassing and evaporation to occur, which may lead to a total loss of the acid, causing damage to the plates. The performance of a lead-acid battery is affected by its temperature. With a low battery temperature, the rate at which the battery can be discharged is decreased because of higher internal resistance. In general, the battery performs better when it is kept warm. As we have already said, when a lead-acid battery discharges, the specific gravity of the electrolyte reduces. This increases the temperature at which the electrolyte will freeze. In very cold temperatures with a discharged battery, there is a risk of the electrolyte freezing and damaging the battery. It is therefore important to maintain the battery in a fully charged state during winter operations. Electrolytes are highly corrosive, and if spilled in aircraft, can cause extensive damage. The neutralizing agent to be used on an acid electrolyte spillage is a sodium bicarbonate solution. In older types of lead-acid battery, the acid is in liquid form, and great care has to be taken to avoid any spillage. More modern batteries are of the absorbed liquid type, where most of the electrolyte is absorbed into the active materials in the plates, making it less prone to spillage. Lead-acid batteries are still used in some smaller aircraft, but have been largely replaced by alkaline batteries of the nickel-cadmium or NiCad type. The plates of these batteries are composed of nickel oxide and cadmium, and the electrolyte is potassium hydroxide. The specific gravity of the electrolyte is in the range of 1.24 to 1.30. Again, the electrolyte can be highly corrosive. The neutralizing agent to be used in case of a spillage is boric acid. However, the cells are all enclosed in a sealed metal container, so the risk of a spillage is very small. The on-load voltage of one cell is approximately 1.2 volts. A 24-volt battery will consist of 20 cells in series and a 12-volt battery of 10. Unlike the lead-acid battery, the voltage variation from fully charged to fully discharged is very slight. Here is a graphical representation of a comparison of a lead-acid battery against that of a NiCad battery during discharge. As you can see, the NiCad battery holds a much more constant voltage during the discharge cycle. Unlike the lead-acid battery, the specific gravity of the nickel-cadmium battery electrolyte does not change, and as we have seen, the voltage variation from fully charged to fully discharged is very slight. The only way to determine the state of charge is to carry out a measured discharge test or capacity test. Nickel-cadmium batteries are not affected by low environmental temperatures, in the way that lead-acid batteries are. And because the specific gravity of the electrolyte remains high, there is no danger of it freezing. A NiCad battery has a low internal resistance. Because of this, it is capable of supplying very high currents during its discharge cycle. This type of battery is often used to drive the starter motor of an airliner's auxiliary power unit. The nickel-cadmium battery normally has a metal case, unlike the hard plastic of the lead-acid battery, so it is more robust. It is also more compact than a lead-acid battery of the same capacity. NiCad batteries can have a problem with the amount of heat generated during charging. In certain conditions, heat is generated faster than it can dissipate, so causing a rapid increase in temperature. This has the effect of lowering the effective internal resistance of the cells, thus allowing an ever-increasing charging current and subsequent increase in temperature, which, unless checked, leads to the total destruction of the battery. This condition is known as a thermal runaway and can cause so much heat that the battery may explode. For this reason, the charging of a NiCad battery must be closely monitored. A built-in thermal switch monitors the battery temperature and operates at a preset temperature, isolating the battery from the charging source until the temperature reduces back to an acceptable level. There may be an indicator light on the flight deck to alert the pilot when the temperature switch operates. As we have already said, the capacity of a battery is the product of the load in amperes that the manufacturers state it will deliver and the time in hours that the battery is capable of supplying that load. The capacity is measured in ampere hours. Actual capacity is determined by the battery's deterioration in service. If a 60 ampere hour battery, when subjected to a 60 ampere load, lasts only 42 minutes, then the actual capacity is 42/60ths, or 70% of its rated capacity. In other words, the battery is only 70% efficient. A capacity test, which is a test to determine the actual capacity of an aircraft battery, is carried out every 3 months, and the efficiency must be 80% or more for the battery to remain in service. This capacity will ensure that essential electrical loads can be supplied for the time stipulated in EASA regulations, following a total generator failure. Essential loads will include aircraft attitude information, essential communication equipment, standby lighting, pitot heat, plus any other services necessary for continued safe flight. Spare batteries will be held ready for use in the electrical workshop. Lead-acid batteries are stored in a charge state to prevent deterioration of their plates. NiCad batteries can be stored in a discharge state with no detrimental effect to the battery, and therefore have a longer storage life or shelf life. The pilot's pre-flight check of a battery may include comparing the on-load voltage with the off-load voltage to give an indication of the state of charge of the battery. If the battery is not supplying any load, then it will show its off-load voltage. If the battery is then loaded up by switching on selected loads and the voltage is maintained, then the battery is in a good state of charge. If the voltage falls below a stated value within a time limit determined by the manual, then the battery is in a low state of charge and should be replaced. As we know, a battery is made up of a number of cells in series. If any single cell should fail, the battery voltage will probably fall to 0. The battery will be unserviceable and must be replaced. A constant voltage charging system using the engine-driven generator is employed with most lead-acid batteries to maintain the battery in a fully charged condition during flight. With this system, the output voltage of the generator is maintained constant, at 14 volts for a 12-volt battery and at 28 volts for a 24-volt battery. With NiCad batteries, which are susceptible to thermal runaway, a dedicated battery charger which monitors battery temperature and voltage is used. Some NiCad battery charging systems use a method known as pulse charging. In this type of system, the battery charger delivers short pulses of charging current. After starting an engine using the aircraft's battery, the generator, when it is online, recharges that battery. This is indicated by the high initial reading on the generator's ammeter or the center zero battery ammeter. This reading should quickly reduce as the battery is recharged. But if the charge rate increases or remains high, it could be an indication of a faulty battery. A continuing high charge rate could result in a battery overheating and subsequent damage. That is the end of the lesson. On screen is a summary of the advantages that NiCad batteries have over lead-acid batteries. The main disadvantage that NiCad batteries have is the more complex charging procedure required to avoid thermal runaway. Spend a moment studying this table, then move on when you are ready. Displayed on the screen is a summary of the two types of battery. Again, spend a moment studying this before moving on. Here are the other important points that you should take from the lesson. A battery capacity test is carried out every 3 months. A battery must display an efficiency of 80% or more to remain in service. The flight deck battery check is carried out on load, which is with the load applied. If one cell fails, the battery is unserviceable and must be replaced. In this lesson, you will learn what a magnet is and how it physically interacts with other magnets. You have probably already seen and used magnets. They appear in many forms. You probably played with magnets as a child, and there are magnets which are used around the house, such as the magnets which are used to stick notes to the fridge door. Legend has it that magnets were discovered by a Greek shepherd who walked across a field containing dark red stones, which pulled the nails out of his sandals. These stones were given the name magnetite or lodestone. Magnetite or lodestone is the most magnetic of all the naturally occurring minerals on Earth. A magnet is an object that has a magnetic field. You may think that this doesn't sound like a very helpful definition of a magnet, but this definition does emphasize the fact that when we call something a magnet, we are not describing what the object is made from, as we do when we say that something is made from metal or plastic, etc. Our definition is really saying that an object is a magnet when it behaves like a magnet. For instance, here is something picking up some common metal objects. It would be reasonable to call this something a bar magnet. If, however, it stops acting like a magnet, we may no longer call it a magnet. So what then are the qualities by which we recognize a magnet? How does a magnet behave? The first thing that we notice about a magnet is that it attracts towards itself ferrous materials, such as iron, nickel, and cobalt, but it does not attract other materials, such as plastic, glass, or even some other metals, like aluminium. The materials that can be attracted by a magnet are termed magnetic materials, or more precisely, ferromagnetic materials. Therefore, magnetism is simply the name we give to that property of an object or body which causes it to act like a magnet. The next thing we need to look at is how a magnet reacts in the presence of other magnets. Two magnets, when placed near each other, either repel or attract each other. This unusual behavior is one of the trademarks of magnets. We can explain this behavior by referring to the concept of magnetic polarity. When we talk about magnetic polarity, we are talking about the north and south poles of a magnet. All magnets possess a north pole and a south pole. You will never find a magnet that has a single pole. When the ends of two magnets are brought together, they either repel or attract each other. If the magnetic poles that are brought together are the same sort of pole, two north poles for instance, then the magnets repel each other. The same thing happens if two south poles are brought together. If one of the magnets is rotated so that its other pole is brought close to the second magnet, then the two magnets will attract each other. So we can say that unlike magnetic poles attract each other. The magnetic effects of a magnet are produced by an invisible force that surrounds the magnet. This force is known as a magnetic field. To discover the layout of a magnet's field, we can suspend a magnet so that it is free to rotate as shown. The magnet under the pencil is free to rotate both clockwise and anti-clockwise. However, in the presence of a second magnet, it does not move about randomly, and it does not stop in just any orientation. The suspended magnet will come to rest pointing in a very specific direction, which depends on its position relative to the other magnet. Let's now view the magnets from above. We will observe and take note of the various directions in which the suspended magnet comes to rest when it is placed in different positions relative to the fixed magnet, to see if there is a pattern to it. If we mark the different directions in which the suspended magnet comes to rest, with arrows pointing from the magnet's south pole to its north pole, it is easier to see the pattern that is emerging. After some time, this picture emerges. The lines that we have plotted are called lines of flux, or lines of force. The lines of flux show the direction in which a freely suspended magnet will come to rest. This direction is referred to as the direction of the field. Notice how the lines of flux are tightly packed together at the poles of the fixed magnet and are much more spread out elsewhere. The regions where the lines of flux are closest together are the regions where the effect of the magnet is strongest. Although in our diagram some of the lines are shown incomplete, they are always a continuous loop, from one pole to the other. We have seen that a freely suspended magnet comes to rest along the field lines of a fixed magnet. But in what direction will it come to rest if there is no other magnet nearby? A freely suspended magnet, even when it appears that there are no other magnets nearby, does not come to rest in a random direction. No matter what direction the magnet is pointing in when it is released and begins its swing, it always ends up pointing in the same direction. This is because the suspended magnet is still being affected by a magnetic field. The magnetic field we refer to is one that everyone on our planet experiences every day. It is the magnetic field created by the Earth itself. The Earth has a magnetic field of its own, which acts as if it is created by a huge bar magnet at the Earth's core. A freely suspended magnet will come to rest aligned with the Earth's magnetic field. The atoms and molecules of magnetic materials behave like micromagnets themselves. It is the total magnetic field from all of these microscopic magnets which gives us the magnetic field we detect around the magnet itself. For simplicity, we will use arrows with points on their north poles to simulate the micromagnets. If the micromagnets are all pointing in the same direction, then their individual fields all reinforce one another. The diagram here shows all the micromagnets pointing in the same direction. A standard bar magnet is just a magnetic material, such as iron or steel, in which some of its micromagnets are pointing in the same direction. If the micromagnets are all pointing in random directions, their fields cancel one another out. So an iron bar, which does not behave like a magnet, is depicted like this, with its internal micromagnets all pointing in random directions. A ferromagnetic material is a material in which the internal micromagnets can be rotated and fixed in alignment with one another. This can be done by stroking it in one direction with the pole of a magnet. Here, the north pole of the magnet is pulled along an iron bar, pulling all of the south poles of the bar's micromagnets into one direction, thereby creating more and more micromagnets which are pointing in the same direction. Notice how the originally disordered micromagnets become aligned as they are pulled into place by the magnet. A magnet where all the internal micromagnets are pointing in the same direction is said to be saturated. It cannot be magnetized anymore. The ease with which the micromagnets are realigned depends on the material in which they exist. The term magnetically soft describes a material in which the micromagnets can be realigned easily. Iron is a typical example of a magnetically soft metal. It can be easily magnetized, but it rapidly loses its magnetic properties. Magnetically soft iron is said to have a low magnetic retentivity. You will not be surprised to learn that a magnetically hard material contains micromagnets which are far more difficult to realign than those of a magnetically soft material. A common hard magnetic material is steel. A hard material is one that requires a lot of effort to magnetize. However, once it is magnetized, a hard material contains its magnetism much longer than a magnetically soft material will. So permanent magnets are made from hard magnetic material. The reason why magnetic materials are attracted to magnets is because the magnet's field aligns sufficient of the magnetic material's micromagnets to turn it temporarily into a magnet with opposite poles. You have learned that the internal micromagnets in a ferromagnetic material can be aligned, causing the object to become a magnet. However, this process can be reversed. The alignment of the micromagnets of a magnet can be broken, so that the object is no longer a magnet. The breaking of the alignment of micromagnets can be achieved in a number of ways. High temperatures can disrupt the orderly alignment of the micromagnets in a magnet, causing it to stop being a magnet. Another way of disrupting the micromagnets of a magnet is simply to drop it onto a hard floor, or to physically strike or knock it. This has the effect of shaking up the micromagnets, randomizing them, and destroying whatever alignment they had within the magnet. A third way is to place the material inside a solenoid, which is supplied with an alternating current. Solenoids are fully explained in another lesson. In the final part of this lesson, we will examine the nature and orientation of the lines of flux when permanent bar magnets are brought together in different configurations, and when a bar magnet is placed near iron objects. Here is the first situation that we are going to consider. On the left is a bar magnet with its north pole pointing to the right, and on the right there is a soft iron bar. If we trace out the lines of flux, we will see that not only are there lines coming from the magnet, but there are also lines coming from the iron bar. This shows that the permanent magnet has induced the micromagnets in the iron bar to align, so that the iron bar is now acting like a magnet. This increases the flux density from what are now two magnets. This property of a magnetic material to increase a magnet's flux density is known as permeability. When the soft iron bar is removed from the magnetic field, it loses most of its magnetism. The little magnetism which remains in the iron bar is known as residual magnetism. Here, two magnets are placed in line, with the north pole of one magnet facing the south pole of the other. The magnets attract each other. If they were not securely fixed in place, they would actually come together. The lines of flux between the two magnets are very tightly packed together. This is because the lines of flux from the two magnets are reinforcing one another to create a dense area of magnetic flux. Here, one of the magnets has been flipped around, swapping over north and south poles. The magnetic lines of flux between the magnets now appears to be deflected. This is caused by the fact that lines of flux can never cross each other. The lines of flux from the north pole of each magnet are pushing the two magnets apart. There is an indication that the two magnets are repelling each other. That is the end of the lesson. Here is a summary of the important points which have been made in this lesson. A magnet is an object which has a magnetic field, and which behaves like a magnet. This magnetic field is characterized by lines of magnetic flux, which trace a path from the north pole of the magnet to the south pole. Like magnetic poles repel each other. Unlike magnetic poles attract each other. For example, the north pole on one magnet will attract the south poles of any other magnets that are brought close to it. Ferromagnetic materials, if they are not magnets themselves, are attracted towards both the north pole and the south pole of a magnet. If a ferromagnetic material has some of its internal micromagnets pointing in the same direction, then that material is itself a magnet. A magnetically soft material has micromagnets that are easy to realign. Less effort is required to magnetize or demagnetize a magnetically soft material than a magnetically hard material. An external magnetic field can induce a ferromagnetic object to become a magnet. Heating a magnet, or physically shocking it, or placing it inside a solenoid which is supplied with an alternating current, can cause the internal micromagnets in that magnet to become unaligned, stopping the material acting as a magnet. The aim of this lesson is to outline the inextricable links between magnetism and electricity. The fundamental aspect of the link between electricity and magnetism is that any flow of electric charge will create a magnetic field. We will now investigate this phenomenon, explaining how the magnetic field may be predicted and put to practical use. In 1820, a Dane named Hans Christian Ørsted observed that a compass needle was deflected away from its north-south alignment when placed near a wire through which a current was flowing. He saw that the compass needle aligned itself at right angles to the wire. When the current was switched off, the compass needle returned to its north-south alignment. Ørsted's experiment revealed that there is a magnetic field around a wire which has a current flowing through it. But this magnetic field has no beginning and no end. This magnetic field has no discernible north or south pole. Further experiments show that the magnetic field around a current-carrying wire is always at right angles to the flow of current, and can be described as being in the form of concentric circles. That is, circles which are of different sizes, but which share the same center. The magnetic field lines always point in a specific direction around the wire, either clockwise or counterclockwise, depending on the direction of the current flow in the wire. A good technique to predict the direction of the magnetic field around a wire is to point the thumb of your right hand along the wire in the direction of the conventional flow of current. Remember, that is the opposite direction to the electron flow. The direction in which your fingers now naturally curl around the wire is the direction of the magnetic field. Because of the similarity between this method of determining the direction of the magnetic field and the direction a right-handed corkscrew needs to be turned to screw it in, the method is called the corkscrew rule. In order to put the magnetic field around a current-carrying wire to practical use, we need to somehow convert the field into something similar to that produced by a bar magnet with a north and south pole. If we look in cross-section at two insulated current-carrying wires placed close together, with the current flowing in the same directions, their magnetic fields will combine, as shown here. If, however, we place two insulated current-carrying wires together with the current flowing in opposite directions, their fields will now interact like this. If we combine both of these effects over a number of wires, we will produce a magnetic field very similar to that produced by a bar magnet. This can be done very effectively by forming an insulated wire into a coil. The two ends of the coil will act as magnetic north and south poles. This device is known as an electromagnet or solenoid. In order to ascertain which end of the solenoid is the north pole, the right-hand grasp rule can be used. If you imagine holding the cylinder in your right hand, with your fingers curling around it in the direction of the conventional current flow, your outstretched thumb will be pointing towards the north pole of the solenoid. There are a number of factors which affect the strength of the magnetic field produced by a solenoid. We have already seen that magnetism is induced in a magnetically soft iron bar if the iron bar is placed within the magnetic field of a permanent magnet. The magnetic field of a solenoid will also induce magnetism in an iron bar. The electromagnet will be especially strong if the iron bar is placed where the magnetic field of the solenoid is strongest. That is, in the center of the coil. Here, the iron bar is the core of the coil, forming a very effective electromagnet which will act exactly the same as a bar magnet. However, the electromagnet can be turned on and off at the flick of a switch. When the current is switched off, the temporarily induced magnetism in the soft iron core quickly dissipates, and it stops acting as a magnet. The strength of a magnetic field produced by a coil is directly proportional to the strength of the current flowing through it. This graph represents visually the connection between the two variables. That is, the current flowing in an electromagnet and the strength of the field produced. As you can see, if the current flow is doubled, then the strength of the magnetic field is also doubled. Another way of increasing the strength of the magnetic field surrounding an electromagnet is by increasing the number of turns making up the solenoid. At a constant current supply, the strength of a magnetic field is directly proportional to the number of turns of wire in the coil which is producing the magnetic field. In aircraft electrical systems, the electromagnet is put to practical use in electrical relays. A relay is simply a remotely operated electromagnetic switch. It consists of a coil with a great number of turns of insulated wire, wrapped around a fixed core of soft iron. In this way, a large magnetic force can be created with a relatively small current flow. A soft metal armature is attached to a pair of electrical contacts, which, in our example here, are spring-loaded to the open position. But when current is passed through the coil, the soft metal armature will be attracted to the core and the contacts will close. When the current to the coil is switched off, the contacts will open again. There is no electrical connection between the control circuit and the circuit being controlled. The contacts of the relay can be used to control high current devices, allowing these devices to be controlled from a small remote switch, thereby reducing the amount of heavy expensive wiring required. Although any electromagnet can be referred to as a solenoid, the term solenoid has a particular meaning in aviation. In aviation, solenoids are used to open and close electrical contacts in a similar way to a relay, or they may be used to open and close valves in the aircraft hydraulic or fuel systems. The primary difference between a relay and a solenoid is that in a relay the soft iron core is fixed, while in a solenoid the core can slide in and out of the coil. With the solenoid de-energized, the core will be pushed out of the coil by the spring. When a current passes through the core will be attracted into the center of the coil, closing the contacts. You will recall that the lines of flux between two opposite magnetic poles look like this, and that the magnetic field around a current-carrying conductor looks like this. If the current-carrying conductor is placed between the two opposite magnetic poles, the two sets of magnetic fields will interact. In the area where the fields are running in the same direction, there will be a strengthened magnetic field. And in the area where the fields oppose each other, the field strength will be reduced. This will produce a force trying to move the conductor in the direction of the weakened field. In physics, this force is known as the Lorentz force. The Lorentz force is felt by all charged particles in an electromagnetic field. It acts at 90 degrees, both to the direction of movement of the particles and to the magnetic field. This is the basic principle on which electric motors operate. Here is a summary of the important teaching points which have been made in this lesson. Any flow of electric charge will produce a magnetic field. The magnetic field around a wire carrying an electric current takes the form of concentric circles, all centered on the wire. The direction of the field around a wire can be predicted using the corkscrew rule. The magnetic field produced by a coil is similar to that of a bar magnet. The north pole of the coil can be found using the right-hand grasp rule. The strength of a coil's magnetic field can be increased by adding a soft iron core, by increasing the current flowing in it, and by increasing the number of turns on the coil. A relay is a remotely operated electromagnetic switch with a fixed core, and a solenoid is a remotely operated electromagnetic switch with a moving core. If a current-carrying conductor is placed between two opposite magnetic poles, a force will be produced which will try to move the conductor. Whenever two materials are rubbed together, electrons may be transferred from one material to the other, causing a build-up of electrical potential in the materials, known as static electricity. This applies to the airframe of an aircraft as it rubs against the atmosphere that is flying through. In this lesson, we will look at how the build-up of static electricity on an airframe in flight is dealt with. And we will discuss how the build-up of static electricity in refueling equipment is prevented. We will also look at how components are protected from electromagnetic interference produced by the operation of other components. The airframe of an aircraft in flight collects electrons from the atmosphere and gains a static electrical charge as it flies through the air. If different parts of the airframe have different levels of static electrical charge, then there is a possibility of a spark being generated between them, leading to the danger of a fire or even an explosion. Any static electrical sparks will also cause interference in the form of static noise or crackling in the aircraft's radio equipment. In order to prevent these problems, all pieces of the metal structure of the aircraft and all components in the aircraft are linked by flexible wire strips. This process is called bonding, and it provides an easy path for electrons to move from one part of the airframe to another, thus maintaining all parts at the same potential. Bonding also acts to maintain the earth return in a unipole electrical system, which is a system using only one wire, with the return current passing through the metal airframe. The unipole system is fully described in another lesson. The static charges that build up on an aircraft during flight tend to accumulate near sharp edges, like the trailing edges of wings and tail surfaces. A static discharge system, consisting of components known as static dischargers or static wicks, is fitted to reduce the build-up of static electricity on the airframe. Static wicks are fitted to the trailing edge of the aircraft control surfaces and the tips of the wings and the tail. The purpose of the static wicks is to provide a conductive path for the excess electrons to flow or leak from the aircraft back into the atmosphere. This transfer of electrons reduces the charge on the aircraft's skin and structure, thus reducing the possibility of interference in the aircraft's radio equipment. Static wicks are fabricated with a wick of wire or a conductive element on one end, which provides a continuous low-resistance discharge path between the aircraft and the air. Static discharge wicks also provide another important safety benefit. In the event of a lightning strike, an aeroplane is designed to conduct the excess electricity through its skin and structure to the wicks, to be safely discharged back into the atmosphere. Though this massive electrical charge often burns or melts the wicks, these devices are simple and easy to replace. Remember though, static wicks do not prevent lightning strikes. They simply help to mitigate the effects. To ensure that no static electrical charge remains on the aircraft after landing, the airframe is brought into electrical contact with the ground as the aircraft touches down. This is achieved by using tyres which contain a high proportion of carbon in the rubber. The tyre and wheel are in contact with the airframe via the wheel bearing, and any static charge is dissipated to earth on touchdown. During refueling, and particularly during pressure refueling, the high fuel flow rates can cause a build-up of static electricity in the refueling equipment. This can cause a difference in electrical potential between the refueling equipment and the airframe, leading to the possibility of a spark being generated with catastrophic consequences. Before fueling commences, the aircraft must be bonded to the fueling equipment, using dedicated wires and clips. This ensures that there is no electrical potential difference between the components, which could lead to sparks. Static electrical charges, radiating from the sparks produced by the constant switching of certain electrical equipment, create interference in radio circuits. This interference is overcome by fitting interference suppressors, usually capacitors, in the cables connected to the source of interference, and by total enclosure of the cables in a continuous metal sheath. This is known as screening. Screening is required for ignition systems, DC generators and motors with commutators, slip ring machines operating at over 200 RPM, and also for any electrical equipment making and breaking a circuit at a frequency greater than 10 cycles per second. That is the end of the lesson. The important points to remember are that bonding of the airframe components reduces the possibility of interference in the form of static noise or crackling in the aircraft's radio equipment, and that static dischargers or wicks fitted to the tips of the wings and tail discharge static electricity back to the atmosphere, thus reducing the possibility of static interference in the aircraft's radio equipment. One of the biggest advantages that an AC supply has over a DC supply is the ease with which the value of alternating voltage can be raised or lowered with great efficiency by the use of transformers. It can also easily be converted into DC by the use of diode rectifiers. Transformers and diode rectifiers are often used together in transformer rectifier units. In this lesson, we will look at the operation of both transformers and diodes. We know from previous lessons that when a current passes through a conductor, a magnetic field is produced, and that the strength of the magnetic field can be enhanced by wrapping the wire in a coil and giving it a soft iron core. We also know that when a conductor is moved through a magnetic field, cutting the lines of flux, an electromotive force is induced in the conductor. It is these principles that are used in transformers. A simple transformer consists of two electrically separate coils of wire wound around two opposite sides of a laminated soft iron core. The coils are known as the primary and the secondary windings. The primary winding is connected to an AC supply, and the output is taken from the secondary winding. The alternating voltage and current in the primary winding creates an alternating flux, which flows through the core and cuts through the coils of the secondary winding. This induces an EMF in the secondary winding, which is available as the output AC voltage. If a load is placed across the terminals of the secondary winding, then an alternating current will flow in the circuit. In electrical diagrams, a transformer is usually indicated by the symbol shown here. The transformation ratio of a transformer is the ratio of the number of turns or coils of wire on the secondary winding, N2, to the number of turns of wire on the primary winding, N1. The transformation ratio is also the ratio of the output voltage to the input voltage. A coil with 100 turns of wire on the secondary winding and 400 on the primary will have a transformation ratio of 100 divided by 400, or 0.25. We can now use this ratio to calculate the output voltage of the transformer. If, in this example, the input AC voltage was 115 volts, the output voltage would be 115 multiplied by 0.25, or approximately 29 volts AC. A transformer with a transformation ratio greater than 1 is known as a step-up transformer, whilst a transformer with a ratio less than 1 is known as a step-down transformer. Transformers are almost 100% efficient in their transfer of power from the primary to the secondary windings. So for all practical purposes, we can say that the power that goes into a transformer equals the power that comes out of it. From this, we can say that the product of the voltage and the current in the primary winding will be equal to the product of the voltage and current in the secondary winding. It is important that the input supply to the primary coil of a transformer is of the correct frequency. Transformers are inductive devices, and if the input frequency is low, it is possible that the transformer will overheat due to excessive current flow. The output of a three-phase AC generator can be transformed by using either 3 single-phase transformers or a 3-phase transformer, which consists of a laminated core with 3 limbs on which are wound the 3 sets of primary and secondary windings. An auto transformer uses a single winding on a laminated core with a pick-off at a predetermined point along the coil. As you can see, part of the coil carries both the primary and secondary current because it is common to both windings. Auto transformers are less expensive than 2-coil transformers because they use less materials. However, one of the major advantages of 2-coil transformers is that the primary and secondary circuits are electrically isolated from each other, and this is not so in auto transformers, so their use is limited to situations where this is not important. Where AC is required for the operation of instruments on the aircraft, auto transformers can be used to either step down or step up the source supply to the required voltage. The supply usually required for instruments is 26 volts AC. A rectifier is a device which will convert alternating current into direct current. The most common rectifier in use in aircraft systems is the solid-state diode rectifier. The electrical symbol for a diode rectifier is shown here. The diode is a semiconductor device, and its operation is fully explained in the lesson on semiconductors. It has a very low resistance to current flow in the direction of the arrowhead and a very high resistance in the other. If a diode rectifier is placed in an AC circuit, it will allow current to flow through the load in one direction only. This is termed half-wave rectification. Current will flow through the load in one half cycle, but in the other half cycle, when the polarity of the voltage is reversed, the flow of current will be blocked. This method of rectification will therefore produce pulses of DC in the secondary circuit, with gaps between the pulses. To produce DC without gaps in the pulses, a full-wave bridge rectifier, as seen on the screen, can be used. The bridge has a diode rectifier on each leg. The AC supply is connected across the bridge at points A and B, and the output is taken from points C and D. In one half of the cycle of the AC input, point A will be positive and point B negative. So current will flow through the bridge and the load in the direction shown. In the next half cycle, the polarity will be reversed, making point A negative and B positive. However, because of the arrangement of the diodes, the current flows through the load in the same direction as before. The output of a bridge rectifier consists of pulses or ripples of DC. These usually need to be smoothed electronically before being used. A much smoother supply, without large peaks and troughs, can be produced from a three-phase supply by using a three-phase bridge rectifier. A three-phase rectifier superimposes the full-wave rectified output from all three phases on top of each other. Thus it produces a much smoother output than a single-phase rectifier. The output of a three-phase rectifier can therefore be considered to be of a steady DC voltage. There is another type of diode rectifier you may come across, known as the Zener diode rectifier. The symbol for a Zener diode is shown here. This type of diode, again, allows unrestricted current flow in one direction, but if the polarity of the voltage is reversed, it will block current flow, until at a predetermined voltage drop across the diode, it will allow reverse current to flow without restriction. Zener diodes are often used in voltage regulator circuits. Transformer rectifier units, or TRUs, convert AC at one voltage to DC at another voltage, in order to supply the DC needs of an aircraft with an AC distribution system. The TRU combines the transformer and rectifier in one unit. The input supply is usually 115/200 volts, 400 Hz, three-phase AC, and the output 28 volts DC. The TRU current output can normally be monitored by the pilot, either on a gauge or an electronic screen. Some aircraft types, which have a frequency-wild AC distribution system, use transformer rectifier units to feed static inverters, to supply the aircraft's normal constant frequency requirements. This is done by using the TRU to change the frequency-wild AC into DC, and then using the DC to power the inverter, which will produce a constant frequency AC output. That is the end of the lesson. Here are the main points that you need to take from it. Transformers are used to raise or lower the voltage in an AC electrical system. An auto-transformer has only one coil. Auto-transformers with an output voltage of 26 volts are often used to power instruments. In a step-up transformer, the output voltage is greater than the input, but in a step-down transformer, it is lower. The power in the primary winding of a transformer is equal to the power in the secondary winding. The input supply to the primary coil of a transformer must be of the correct frequency. If the input frequency is low, it is possible that the transformer will overheat due to excessive current flow. A diode rectifier has a very high resistance to current flow in one direction and a very low resistance in the other. A bridge rectifier produces an output of full-wave rectified DC. A three-phase bridge rectifier produces a steady DC output voltage. A Zener diode acts in the same manner as a normal diode until a predetermined reverse voltage is reached, at which point it allows unrestricted current flow in the reverse direction. Transformer rectifier units, or TRUs, convert AC at one voltage to DC at another voltage, in order to supply the DC needs of an aircraft with an AC distribution system.
In this lesson, we will look at the construction and operation of electric motors using AC as their power supply. The great advantage that an AC motor has over its DC counterpart is that it doesn't require the use of a commutator, so the problems of arcing at the brushes is greatly reduced or even eliminated. Whether the AC motor is single or multi-phase, the principle of operation is the same. The motor is made up of a stationary part known as the stator and a rotating assembly known as the rotor. The stator is most commonly fed from a three-phase AC supply. The stator windings are set 120 degrees apart, with the pair of poles for each winding being supplied from one of the three phases. This arrangement produces a rotating magnetic field around the stator. To see how the rotating magnetic field is produced, we will look at one half cycle of the AC supply. When the current flow in their phases is positive, the poles marked A, B and C are magnetic north poles, and those marked A1, B1 and C1 are south poles. When a phaser's current flow is negative, its magnetic poles are reversed, with A1, B1 and C1 becoming magnetic north poles and A, B and C becoming souths. If we start at point 1 on the graph, you can see that phase A is at its positive peak, so pole A has a strong north magnetic pole and A1 a strong south pole. Phases B and C are both negative, so poles B1 and C1 have weaker north poles. The magnetic fields will look like this. If we move the sequence on to part 2, we can see that the C phase current is now at its negative peak, so the C1 to C magnetic field is at its strongest. A phase has moved away from its peak, so the strength of the A and A1 magnetic poles is reducing, and B phase has moved from negative to positive. So now pole B is now a north and pole B1 a south. Moving on to position 3, B phase is now at its positive peak, so there is a strong magnetic field from pole B to B1. Both A and C phases are negative, so poles A1 and C1 are weak norths. At position 4, A phase is now at its negative peak, so there is a strong magnetic field from pole A1 to A. B and C phases are both positive, so poles B and C are weak norths. This process continues as each phase moves through its cycle, causing the total magnetic field to rotate at a speed equal to the frequency of the supply. If two phases of the supply to a three-phase rotating field are reversed, the direction of rotation of the field, and thus that of the rotor being driven by it, will be reversed. There are two types of rotating field AC motors in common use in aircraft installations. They are known as synchronous motors and induction motors. We will look at them both, beginning with induction motors. The induction motor gets its name from the fact that an alternating current is induced in the rotor by the rotating magnetic field in the stator. It is the most commonly used AC motor because of its simplicity, its robustness, and because it is relatively cheap to produce. The rotor usually consists of a cylindrical laminated iron core which has a number of longitudinal bars of copper evenly spaced around the circumference. These bars are joined at either end by rings of the same material to form a composite structure called, because of its shape, a squirrel cage. The rotor bars are made of very low resistance material so that a large current can flow through them. The rotating magnetic field produced in the stator cuts through the bars of the rotor, which along with the end rings form a closed circuit of low resistance. The resultant induced voltage creates a relatively large current flow in the squirrel cage assembly, as shown in this simplified diagram. This current flow sets up its own magnetic field, which interacts with the rotating field of the stator to produce a torque, causing the rotor to turn in the same direction as the rotating field of the stator. The speed of an induction motor is determined by the frequency of the supply and the load on the motor. The rotor never quite reaches the speed of the rotating field. The reason for this is because if it did, then the squirrel cage bars would not be cut by any lines of flux from the rotating field, and no voltage would be induced in them. The difference between the speed of the rotating field, or the synchronous speed, as it is known, and rotor speed is called the slip speed, or rotor slip. Because of the difference in speed between the stator field and rotor, the induction motor is sometimes referred to as being asynchronous. If the load on the motor is increased, the rotor will tend to slow down. This will increase the amount of cutting of lines of flux and increase the current flowing in the squirrel cage, which in turn increases the strength of the induced magnetic field, which increases the motor torque to compensate for the increased load, maintaining the motor speed virtually constant. Most induction motors fitted on aircraft are of the three-phase type. However, single-phase induction motors can also be used. Single-phase induction motors are not self-starting. That is to say, when power is applied, they will not rotate. The most common method of starting a single-phase induction motor is by use of a split-phase winding at 90 degrees to the main winding. The current in the split-phase winding is made to lead or lag the current in the main winding by 90 degrees in order to change the pulsating field into a rotating one. This can be done by the use of capacitors, inductors, or resistors. Occasionally, the failure of one phase of the supply to a three-phase induction motor does happen. If the motor is lightly loaded, then it will probably continue to run at about half its normal speed. The fault usually becomes apparent the next time an attempt is made to run the motor, when it will not start to rotate. If a bar magnet is suspended in a rotating magnetic field, it will lock into the field with its south pole staying with the rotating north pole and its north pole staying with the rotating south. The magnet will therefore rotate synchronously with the field, at the same speed as it. This is the principle of operation of the synchronous motor. A practical synchronous motor, rather than using a bar magnet, has a rotating coil on a soft iron core, energized with DC through slip rings, causing it to act as an electromagnet. In the same way as the bar magnet did, it lines up with the field created by the stator, and if the field turns, the rotor turns with it. The speed of rotation of a synchronous motor depends upon the frequency of the supply and the number of poles. Since in most cases the supply frequency is constant, then so is the motor speed. We can transpose the formula we use to calculate a generator's frequency to work out the speed of the motor in revolutions per minute, or RPM. If a synchronous motor with 4 poles is supplied with a constant frequency 400 Hz supply, It will rotate at a constant 12,000 RPM. One disadvantage of the synchronous motor is that it is not self-starting. To obtain the initial rotation, some induction windings have to be added to the rotor to assist in bringing it up to synchronous speed. This is often achieved by fitting a squirrel cage type assembly to the rotor. Synchronous motors are often used on aircraft to indicate engine RPM. A small three-phase AC generator, known as a tacho generator, is driven by the engine, so that the frequency of its output will be directly proportional to engine speed. The electrical output is used to drive a synchronous motor in the RPM indicator. The operation of this instrument is fully explained in the instrument's lessons. That is the end of the lesson. Here is a summary of the main points. An AC motor is made up of two parts, a stationary stator and a rotating rotor. AC motors use a rotating magnetic field in the stator to drive the rotor. If two phases of the supply to a three-phase rotating field are reversed, the direction of rotation of the field, and thus that of the rotor being driven by it, will be reversed. An alternating current is induced in the rotor of an induction motor by the rotating magnetic field in the stator. The difference between the speed of the rotating field of an induction motor and the speed of the rotor is known as the slip speed or rotor slip. In a synchronous motor, the rotor rotates at the same speed as the rotating field. Here is the formula for calculating the speed of rotation of a synchronous motor.
Semiconductors have had a monumental impact on our society. Semiconductors are used to make microprocessor chips, as well as being used in the production of diodes and transistors. Semiconductors are at the heart of all electronic devices. Modern aircraft use electronic components in many of their systems, including automatic flight controls, navigation and engine control systems. In this lesson, we will look at what a semiconductor is, and at the makeup and operation of diodes and transistors. We will begin the lesson by reviewing the atomic construction of conductors and insulators. The simplest atom is the hydrogen atom. It consists of a nucleus containing one proton, positively charged, with one electron, negatively charged, orbiting about the nucleus. Conductors and insulators have more complex atoms, with greater but equal numbers of protons and electrons, with the latter orbiting the nucleus in multiple orbits or shells. The nuclei of all atoms, except hydrogen, also contain neutrons. They play no part in the electronic process, so we can ignore them. The electrons in the outer shell of an atom are known as the valence electrons. Electrons in the outer shells may be less tightly bonded to their parent atom than those on the inner shells, and are free to move from one atom to the next. These valence electrons, known as free electrons, form the basis for electrical current flow within the material. Conductors possess large numbers of free electrons. This allows current to flow easily through the material. Gold, silver and copper are all examples of good conductors. Insulators possess few free electrons. This means that it is difficult to get current to flow through them. Mica and glass are examples of good insulators. Semiconductors, as their name would imply, fall somewhere between conductors and insulators. Silicon and germanium are the two semiconductor elements that are used in the production of electronic components. By far the most commonly used is silicon, which is a very common naturally occurring element. It is, for instance, the main element in sand. Silicon and germanium, along with carbon, have a unique property in their electron structure. Each has 4 valence electrons in its outer orbit. As shown in this simplified diagram, the 4 electrons form perfect bonds, known as covalent bonds, with 4 neighbouring atoms creating a lattice. All of the outer electrons in a pure silicon or germanium crystal are involved in perfect covalent bonds, so they can't move around. A pure silicon or germanium crystal is somewhere between a conductor and an insulator. Very little electricity will flow through it. You can change the behavior of silicon or germanium and make it into a conductor by a process known as doping. In doping, a very small amount of an impurity is mixed into the silicon or germanium crystal. Doping produces 2 new materials, known as N-type and P-type material. In N-type doping, antimony or arsenic is added to the semiconductor material in small quantities. Antimony and arsenic each have 5 outer electrons. So when they get into the silicon or germanium lattice, the 5th electron has nothing to bond to, so it's free to move around. As you can see in this simplified diagram, when an EMF is applied, the free electrons move through the material from atom to atom, creating a current flow. N-type material is a good conductor. Electrons have a negative charge, hence the name N-type. However, it should be noted that the material itself remains electrically neutral. There are always an equal number of protons and electrons within the material. In P-type doping, aluminium or indium, each of which has only 3 outer electrons, is the dopant. When mixed into the semiconductor material lattice, they form holes in the lattice where an electron has nothing to bond to. Holes can appear to conduct current. A hole happily accepts an electron from a neighbour, moving the hole to the neighbouring electron. As you can see in this simple animation, when an EMF is applied, the hole appears to move through the material from right to left, causing an electron flow in the opposite direction. The absence of an electron creates the illusion of a positive charge, hence the name P-type. P-type semiconductor material is a good conductor. Again, it should be noted that it possesses no electrical charge, there being an equal number of electrons and protons in the material at all times. A junction diode, which consists of a piece of N-type material fused to a piece of P-type material, is the simplest possible semiconductor device. In this diagram, we're using white circles to indicate holes, and green dashes the free electrons in the 2 materials. At the junction of the 2 materials, some free electrons from the N-type material migrate across the boundary to fill holes in the P-type, and similarly, holes migrate the other way. This migration produces positive ions in the N material and negative ions in the P material. This in turn produces a charged region at the junction, known as the depletion layer, and creates an electrical potential, known as the barrier potential, across the junction. The positive and negative ions in the depletion layer repel holes and electrons, preventing further electron or hole movement between the materials. The barrier potential may be represented as an imaginary battery, although it should be remembered that the regions of increased positive and negative charge exist only across the junction. The material as a whole possesses no electrical charge. If we now connect an external EMF across the material, with the positive terminal connected to the N-type material and the negative terminal to the P, electrons will be attracted to the positive terminal and will be pulled from the N side of the junction. Similarly, holes will be attracted away from the P side of the junction towards the negative terminal. This increases the number of positive and negative ions, deepening the depletion layer. Apart from a very small leakage current, this deepening of the depletion layer prevents current flow across the junction. The junction is said to be reversed biased. If the polarity of the external EMF is reversed, so that the positive terminal is connected to the P-type material and the negative terminal to the N, the holes in the P-type material will now be pushed to the right, towards the junction, and the free electrons in the N-type to the left, again towards the junction. In the junction region, the free electrons and holes combine. Thus the barrier potential is overcome, and current will flow freely through the junction. In this configuration, the junction is said to be forward biased. The junction diode then acts as a rectifier, allowing current to flow through it in one direction only. As a reminder, here is the electrical symbol for a diode rectifier. We will now look at the bipolar or junction transistor. There are two types of junction transistor. They are known as the NPN transistor and the PNP transistor. The NPN transistor consists of a thin layer of P-type material sandwiched between two pieces of N-type material, whilst the PNP transistor has a thin layer of N-type material sandwiched between two pieces of P-type material. The three regions of either type of transistor are known as the collector, the base, and the emitter. The circuit symbol for each transistor is shown here. As you can see, the symbols differ only in regard to the direction of the arrow between the base and the emitter. The arrow always points in the direction of conventional current flow. For an NPN transistor, it points from base to emitter, and for a PNP, from emitter to base. The theory governing the flow of current in a transistor is complex and beyond the scope of this course, so we will limit ourselves to a very basic explanation of the operation. We will have a look at the operation of the two types of transistor, beginning with the NPN type. If we apply an EMF across the collector-emitter region of an NPN transistor, as shown here, remembering back to the junction diode, one of the junctions will be forward biased, but the other will be reverse biased, so no current will flow in the circuit. However, if we apply a small EMF, known as a bias voltage, across the base emitter region, changes take place in the material which will allow current to flow freely from the collector to the emitter. The ability of a transistor to control a large collector-emitter current by means of a small base emitter current means it can act as a switch or electrical relay by turning the small base emitter EMF on and off, thus controlling the current flow in the collector-emitter circuit. The transistor can also act as an amplifier. If a small AC voltage signal is superimposed on the bias voltage, it will produce directly proportional variations in the collector-emitter current. A PNP transistor's operation and function is similar in all respects to that of an NPN transistor, except that the polarities of the applied EMFs are reversed. So now the conventional current flows from the emitter to the base, and from the emitter to the collector. In conjunction with the junction diode and other electronic components, such as resistors, capacitors, and inductors, the applications for the transistor are almost limitless. Furthermore, the ability to control precisely those areas to which doping is applied means that all of these components can be incorporated into a highly sophisticated and complex circuit within a single small piece of silicon or silicon chip. That is the end of the lesson. Here are the main points. Semiconductors, as their name would imply, fall somewhere between conductors and insulators. Germanium and silicon are the two semiconductor elements that are used in the production of electronic components. You can change the behavior of silicon or germanium and turn it into a conductor by a process known as doping. In N-type doping, antimony or arsenic is added to the semiconductor material in small quantities, producing free electrons. In P-type doping, aluminium or indium is the dopant. This produces holes in the lattice structure. A junction diode consists of a piece of N-type material fused to a piece of P-type material. A junction diode allows current to flow freely through it in one direction, but resists current flow in the opposite direction. A transistor can act as either an electrical switch or as an amplifier.